Hello and welcome. Today we're going to look at distributions for quantitative data. But before we begin, I just want to go over a few things. One, you'll want to have a calculator available and handy. There'll be times where you'll need a calculator to work out examples, or as we go through examples, you want to make sure that you're able to plug in the values and get the same results. And also, two, this is a video, so keep in mind that you can pause the video at any time. You can rewind the video to rewatch if you miss something. And three, there will be times where we'll do examples, and I'll ask you to actually pause the video, and I'll say pause the video here and try the next example. So I want you to actually pause and try the example on your own, and then when you're done with it, hit play, and we'll continue going over it. So let's begin. We're going to look at two different types of variables right now. The first, a categorical or qualitative variable, names categories and answers questions about how cases fall into those categories. So let's look at some categorical examples. One example might be gender. Another might be ethnicity. So those would be categorizing it, categorizing people into genders or ethnicity. We could do, what else could we do? We could do hair color, eye color, any of those as just examples. Our focus is going to be quantitative data, so a quantitative variable is naturally measured as a number for which meaningful arithmetic operations make sense. Units tell us how each has been measured. So what this means is it has to be a number, but that's not enough to mean that it has to be just a number. But it has to be a number to where if you make any kind of or do any kind of arithmetic operation on it, the results will have meaning as well. And usually we could say that it's a number that has to have units. So let's look at some examples. Examples of quantitative data would be, maybe we're going to analyze people's weights. Maybe weights in pounds. Maybe we want to look at people's heights in inches. Maybe we want to look at salary or income in dollars. So these would be examples of quantitative data. Notice that these are all number values and they have units. Now let's consider another example. What if I said zip code? Do you think zip code would be a categorical or a quantitative variable? Now true that zip code is a number, but I want you to think now if you took all the students in the room or everybody in a room and you averaged up their zip code, is that going to tell you where the average person in the room lives? No, right? So that wouldn't have really any meaning to take the average of that. So zip code is actually a categorical variable. So just to keep in mind, just because it's a number does not mean that it's going to be quantitative. All right, let's look at some ways to show quantitative data. Let's look at a dot plot. So a dot plot is a simple display. It just makes a dot along an axis for each case in the data. Now this kind of just looks like a table, right? But just think of it as still that if this was the axis and these were the number, in this case we're looking at die rolls. So the dot plot above shows the number of times out of 50 that Jill rolled a 1 to 6 with a single die. So we're just looking at die rolls, and 1, 2, 3, 4, 5, 6, and then here we have the results. So think of that as this would be kind of like a dot plot. So if we look at this, what does each dot represent? Well, each dot represents one of Jill's rolls, right? So this represents one of Jill's rolls of the die, right? How many dots are there in total? Well, we could go through and count all these, right? But if we look here, it just says out of 50, right? And up on the top, you could see that it says 50 as well, but we could definitely count these up. Let's go ahead and count these up. If we count these up, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Notice here we can go to 6, 7, 8, 9. 7, and that's 7, 8, 9, 10, 11, 12, 13, 14. So if you add all these up, you should get 50. All right. How many dots are in total? Well, we just looked at that. There's 50. And how many times did Jill roll a 2? Well, we can see these are the rolls 2, and she rolled a 2 4 times. Now, does one of the dots tell me which roll it came from? Now, do I know what roll this was? So if I look at this first dot on the 2, do I know what that is? Do I know which roll that was? Was that the 5th roll, the 10th roll, the 2nd roll, the 1st roll? I don't know, right? So this, no, it just says just that it happened. So this is kind of more of like a vertical alignment, and most of the times you'll probably see a dot plot in a horizontal alignment. So let's go ahead and draw one briefly. We may not finish this, but we could definitely. So let's make sure that this is equally spaced. So we have 1, 2, 3, 4, 5, 6. So these will be the die roll results. And let's just put it. How many ones did she roll? She rolled 10, right? We're not going to put an axis here for labeling, so we're just going to put a dot for each roll. So we have 10 ones. Nine, 10. So we'd have 10 rolls there. How many 2s did she roll? She rolled 4, so we'd put 1, 2, 3, 4. How many 3s? 3s, she rolled 6 3s, so 1, 2, 3, 4, 5, 6, and so on. So we can see that we're just going to build this dot plot as we move across. I probably don't have enough room here for the last one since there's 14 in that one, and this was at 10 already, so we're definitely going to go over. I'm trying to keep everything equally spaced because I don't want to cluster these. I kind of want to keep everything looking the same. How many do we have here? 6, 7, 8, 9. And then 7 5s, 1, 2, 3, 4, 5, 6, 7, and 14 6s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and we'll put it up there, 14. So, and this would be another orientation. This is how most times you'll see a dot plot. All right, let's continue. When we describe data, we say it's the distribution of the data. So here are things where it says write a summary analysis or describe the distribution of the data. And when we're looking at that or analyzing that, we're really looking at describing the patterns. So when we describe patterns, we talk about the overall pattern, in which case we're going to talk about 4 key components. We're going to talk about the shape of the distribution, the center of the distribution, the spread of the distribution. And things that don't really fit into the pattern, these are called outliers. So get used to thinking about that when you're describing something: shape, center, spread, outliers. And this is kind of the big picture of what we're looking at right now. So keep this in mind, that the things we're looking at relate to these four components: shape, center, spread, outliers. Well, let's start with shape. We have four shapes we're going to look at. We're going to look at uniform. And uniform, notice how it pretty much kind of looks flat, right? It's kind of like the same all the way across. It doesn't have to be perfectly flat, but it looks all about evenly distributed, right? Equally distributed among all the values. Pretty close. Next we have normal, bell-shaped, or symmetric with a central peak. So I'm just going to draw around. Just this is kind of a good idea to do, so you can start seeing, okay, this looks like a nice hill, right, with peak, and then it goes what, equally to the left and right. So it tails off left and tails out right about the same amount. Then we have skewed to the left or left skewed. So you'll hear it as left skewed. Sometimes you might see negatively skewed, depending if you're looking in other textbooks or watching videos or looking on the web. So left skewed or negatively skewed. So this one, this clusters on the right, and it tails off here to the left. And then right skewed or positively skewed, here we see the data clusters on the left and it tails off to the right. So these are the four kind of key graphs we're going to look at: uniform, symmetric with the central peak, left skewed, and right skewed. And you could use any of this terminology: normal, bell-shaped, symmetric with the central peak. So let's describe each of these. How would we describe each of the graphs above? Well, uniform, what does uniform look like? Looks kind of flat. I might say evenly spread out. Remember, write down things that make sense to you. How would we describe symmetric with a central peak, bell-shaped, or normal? I might say that this has a cluster in the middle. And then I might put it tails off to the left and right. So a cluster in the middle, tails off to the left and right. Left skewed, I look at the data clustering on the right. And it tails off to the left. So remember, the skew is where the tail is going. If it's tailing off to the left heavily, then that would be left skewed. And then likewise, if it's tailing off heavily to the right, then we'll say that's right skewed. So I'll put a cluster of data on the left. So I'll say it's cluster, there's a cluster on the left. And then tails off to the right. Now the graphs I put up here are really straightforward, and just keep in mind that data is not always going to look so nice and neat like that. And you'll learn in class, ways, how do we analyze it? When if it's in between, what do I do? So just something to think about, that not all data is nice and neat, like these ones up above. So that was looking at all the shapes. Remember, shape, now what are we going to look at? We're going to look at center. So what is center? A center, or the center, is a single value, so keep in mind it's just one value. So it's a single value used to represent a typical data point. A typical or average data point. So what do I mean by that? So let's consider that you're in class, right, and you look at your class, and, well, maybe we have a bunch of values, right, and you say, well, what looks like a good middle or typical value of people in your classroom? Maybe you take the average, and you look at it and say, you know what, I have a lot of people in the class, and maybe the average comes out to 5'6". So I'm going to say, you know, that looks like a good value that represents the class as a whole. So I would say the typical person in our classroom is 5'6". So even if nobody is 5'6" in the room, but it's the kind of like that middle number, because you may have, well, there's a lot of people ranging from, you know, 5'3" to 5'8". And you know what? It looks like 5'6" is a good value that I could use to represent the class as a whole. So that is our view on center. Let's look at spread. Another word for spread you're going to hear is variability. So it might say analyze the spread or analyze the variability of the data set. Just get used to seeing both. You'll probably see more of the word variability in statistics. So, but variability, spread. Let's move on to the next page. So we're looking at spread still, so we can look at overall range. And overall range is just the max value in the data set minus the minimum value. Max minus min, that's the overall range. It just says all the data is within this much of each other. All right, we have overall range, but most often we're going to want to look at a typical range. So a typical range, well, we use the smallest and largest value of where most of the dots clustered, or in the middle, we should say. And it's a range of values that captures at least the middle 50% or more of the data. That doesn't mean captures all the data. We're just kind of seeing, like, where do most people fall? You may look at your class and say, well, the shortest person is 4'10", the tallest person is 6'4". But I don't say typically people are between 4'10" and 6'4" in the class. Well, no, that encompasses everybody in the class. I might say that it looks like most people in the class are 5'3" to 5'8". That would be a typical range. I'd say typically most of the people in the room, or typically people in the room, are from 5'3" to 5'8" feet in height. So shape, center, spread. And the last one is outliers, but we'll look at outliers a little bit later. There's no real formal definition. Just remember, it's a data point that is unusual. Now, that doesn't mean it's bad, just means it's unusual. All right, histograms. We've talked about dot plots, and if we're looking at a dot plot, we could separate the dot plot graph using bins. So we can bin up data points. So a histogram uses bars and are good for dealing with a lot of data. Histograms have bins, and the look of the graph can change drastically depending on how big the bins are. How do we do it? We divide the entire range of values into equal with piles. These piles are the bins. And the height of each bar tells us how many data points are in that corresponding bin. So the standard rule of thumb for a value that falls exactly on a boundary is to put it into the next higher bin. So for example, we're going to look at earthquakes below. An earthquake of magnitude 5.2 would be put into a bin that goes from 5.2 to 5.4 instead of the bin that goes from 5.0 to 5.2. So what does that mean? Just think of it as if I had this division and I had 5.0, 5.2, and 5.4, and I had a data point right here, and I'm thinking of, well, which kind of pool is this in? If I had two bins here, where does this data point fall? Is it counted in this bin, or is it counted in this bin? And that's what I mean by it goes into the next higher bin. So if it's on the boundary line, it's really counted as part of this bin. So I know it's in this kind of area, or this pool. The bins and the counts in each bin give the distribution of the quantitative variable. So let's look at an example, and then we'll go through talking about the shape, center, spread, and outliers of the distribution. So here is a histogram of earthquakes associated with tsunamis as of July 2015. And in this distribution, we have 1,274 earthquakes represented. So if we look at this is a histogram. So we have the magnitude of the earthquake down here, and over here we have the number of earthquakes. And this is what I mean by the bins. You can see these bars, and we can see that the height of the bar, so like this one here, looks like about 170. So this would tell me that there are 170 earthquakes in this bin in the 7 to 7.2 range of magnitude. So let's look at the shape, center, spread, and outliers. So how would you describe this shape? And if you need to flip back and use those as a reference, those graphs we did on the second page. So if we looked at this, and this is where I think the drawing does help, I'm just going to draw kind of over. Keep this smooth, you don't run into the cracks, and I'm just drawing this to keep it over all of the data. What does that look like? That looks like it's tailing off to the left, so this would tell us that this is left skewed. And let's look for a center. What looks like a good middle representation for the data? Now, we wouldn't say like here's the middle, right? Like this is 6. Well, no, that's the middle over here, but we want to use what looks like a good measurement for what's a typical earthquake measurement. So I'd probably say right around here looks pretty good. This looks like a nice middle, and if by middle I mean, if I looked at this, does this look like there's an equal number of data on the left and the right? Well, looks a little heavy right here, but keep in mind that this is going all the way to the left. So if we added up all these earthquakes, it should be approximately this. So we should be in the ballpark right around 7. So I'd probably say a center of 7.0 would represent the center of the distribution. And let's look at spread and outliers, shape, center, spread, outliers. Now spread, we have kind of two types of spread right now. So we have range we're going to look at. And range, remember, was the max minus the minimum value. But we want to be careful when we're looking at bins when we talk about how we word our responses to these questions. So let's look at here. This is a little bit hard to see. I'm going to just zoom in. If I can, I cannot zoom in, so it's all right, we could deal with it. So first of all, let's look at the scaling and see how does the scaling look. So if we look at the scaling, we can see here it's going from 6 to 7, and there's 1, 2, 3, 4, 5 bins in between. So to go up to 10, that means we'd have to go by, that's 5 increments. So 5 increments would be 20%, right? 20, 40, 60, 80, 100. So this would be at 6.2, 6.4, 6.6, 6.8, and then 7. So that works. So let's count here. This would be 9, 9.2, 9.4. So it looks like the end here is 9.6, and over here this looks like 3.2. Now, we want to be careful when we look at this and say, well, the max is 9.6 and the minimum is 3.2. Well, just because it goes out this far, does that mean there's an earthquake that's 9.6? So remember when we talked about binning, we said that if it's on the boundary line, right, it's in the next higher bin, but there's something else to consider. So I'm just making this up. This isn't part of the data set. I'm just making up an example to think about. So maybe we have this bin here, and I look in here and I say, well, how many data points are in this bin? Well, the height's 3. So I know there's 3 data points in this bin from 5 to 10. Now, do I know where the data points are? Can I for sure say there's a 5, a 6, a 7? No, right? I don't know where, or we don't know where the data points are in here. All I know is that there are 3 data points in here. I might say this is a swimming pool and I know there's 3 people in it, but I don't know where they are at any given time. So this, I don't know. Maybe they're all, it's very possible, right? This is one possibility that all 3 data points are 5. Remember, that would be in this bin. So I can't say for sure that there's any data out closer to the 10. So how do we handle this max minus min? We just say that we can estimate, and that's just being careful, right? We can estimate the range to be, and we're estimating it to be 9.6 minus 3.2. So if we subtract those values, if we subtract, I'm just going to do that over on this side, to be 9.6 minus 3.2, that's going to give us 6.4. So I'm going to put this in parentheses just to represent our calculation. So what does that tell me? That tells me all earthquakes in this data set are estimated to be within 6.4 of magnitude of each other, right? So that's our range, but more importantly, we'd like to look at a typical range. This will help us get a little bit better idea of the data. So if we look at typical range, well, where do typically most of the earthquakes fall? Now we could look at this and say, oh, 5 to 9, right? 5 to 9 would definitely give us where most of the earthquakes are, but we'd like to narrow that down a little bit more, because 5 to 9 is almost, that's getting close to almost all the data. What I'm looking for is, where do I get at least 50%, right? The middle half or more of the data. So that's kind of what I'm looking at here. And I'm like, well, we're centered around 7, so I'm just kind of thinking, I don't know, what looks good to you? We could say 6 to 8. That's pretty good. I think we can kind of get at least half and maybe move in a little bit more. How does that look? Does that look like it gets at least half of the data? I think that does. So this looks like it's going from 6.4 to 7.2468, so 7.8. So what can we say? We can say typically most earthquakes had magnitudes ranging from 6.4, can write that a little neater, from 6.4 to 7.8. So that gives me a better idea in saying, well, most earthquakes were in this range, rather than saying 3.2 to 9.6, because that's much wider. I'm very interested in where most of the earthquakes, what's their magnitude. And outliers. Are there any data points? Now, outliers, remember, are those data points that don't really fit in with the rest, so they're kind of extreme or unusual. So it's kind of hard to tell. We will have formal measurements later on for determining this, but right now we can definitely give a visual inspection and say, what looks unusual? Well, it looks like it's tailing off to the left, right? So does this data point, do these data points look unusual? That's kind of far out. How about this? This is also kind of far away. How about this? Yeah, that looks far away. That looks pretty far. That looks, I'm not sure now, right? We're starting to hit that gray area and saying, well, how far away is far enough? And as I said, later on we'll have formal measurements, but for now we're just going to estimate. So are there outliers? We could say there appear to be some outliers, and where do they range from? So I might say, I don't know, I think these look kind of unusually far away. And to the right, that might be a little far out, but definitely I can think those are. This is about equal here. So I'm going to go with these ones. And it's just a visual inspection of what looks unusually far out. So I would say that there appear, let me scoop this up. I'd say there appear to be some outliers. There appear to be some outliers. And where are they at? Some outliers in this data set or in this data. So these outliers appear to be the earthquakes. Remember, we're analyzing magnitudes. Let's put that detail in there. To be earthquakes with magnitudes below 4.6. Oh, sorry, we should analyze 4.24, 4.6 it looks like. All right, so we've analyzed the shape, the center, the spread, and the outliers. All right, let's look at another histogram, and let's do another analysis on it. That we're not going to look at shape, center, spread, and outliers. Let's answer some questions about it. Given the following distribution of heights of black cherry trees, answer the following questions. So question number 1 says how many cherry trees are measured in this sample? Well, remember the heights of the bins tell us how many trees there are. So we have 60 to 65 here, and the heights to number of trees are over here. We have the height in feet down here. So how many trees? We have 2 trees in this bin. Looks like 3 trees in this bin. 6 trees in this bin. This has a height of 8. 8 trees in that bin. 9. And this looks the same as this one, so 3 trees. So if we add all these up, 2 plus 3 plus 6 plus 8 plus 9 plus 3, you should get 31 trees. Okay, I'm going to scoot this down just so I can fit all the questions on here. All right, let me relabel real quick. We had 2 in this bin, 3, 6, 8, 9, 3. So we already answered the first one. We had 31 trees in this. 31 total trees. Now, how many trees are less than 70 feet tall? So less than 70. So we're looking at, well, here's 70 and we want less than, so we're looking to the left. So how many trees are to the left of that? We have this bin and this bin. So we have 2 plus 3, which would equal, so we have 5 trees that are less than 70 feet. Approximately how many trees are between 65 to 75 feet in height? Remember, if you feel comfortable with this, pause it and work through these problems. I'm going to continue through. So approximately how many trees are between 65 and 75? So we have from here 65 to 75. Now I know that 75, remember, it's on the boundary line, and that means that that would fall into this bin, but we're not counting this bin. So that's why I'm using a word like approximately between this and this. So I don't want to go into this bin because that would add all the trees here, right? That gives you kind of a higher chance for some error in that calculation. So keep it simple. Between 65 and 75, that's 3 and 6. That'll give you 9. How many trees are at least 80 feet tall? So what does it mean to be at least 80 feet tall? Well, at least 80 feet tall. If I said you're at least 5 feet tall, what does that mean? That means you're 5 feet tall or more, right? So this means at least 80 means that you're 80 or more feet tall. That's the trees we're looking at. So here we have our 80 or more. So we're looking at that direction. So that's 9 in that bin, and then 3. So that'll give us 12 trees are 80 feet, at least 80 feet tall. Now another way this question could be asked, what percentage of trees are at least 80 feet tall? So revisiting percentages, remember percentages saying the percentage is the number of things that you're looking at over the total that you have, right? If I said what percentage of the class are male, then you would say, well, that's how many males there are, depending on how many males divided by the total number of students in the class. The same thing here, how many trees are at least 80 feet tall? Well, we have 12 trees over a total of 31 trees. So you want to punch this into your calculator, and I'm going to take this out to 4 decimals. And this is just a way to say approximately, since we will be rounding. So getting this, you should get 0.3871. Now why do we have a 1 here? Remember this was a 0, right? But there's a 9 on the end, and that 9, remember, rounds that 0 up to a 1, because we're going to 4 decimals. Well, that puts it in decimal form, but we want to know what percentage. So what percentage is this? How do we turn decimals into percentages? So remember, we're going to move the decimal two places. Which way? 2 places to the right. So if we move this 2 places to the right, we have 1, 2. So we're going right 2 places. This will give us 38.71, and now we have our percentage. All right? And just to kind of think of things in perspective, this is 12 out of 31. Well, 31 is close to 30, half of 30 is 15. 12 is less than that, right? So I expect this to be less than 50%. 38%, 39% seems pretty reasonable. So at the end, think about your numbers and see, does your percentage kind of make sense with it? I wouldn't say 3.8%, right? That's really close to not very much, and 12 is a good chunk out of 31. All right, last one. What percentage of trees are less than 75 feet in height? So less than 75 feet, well, same thing, we're doing percentages. We already know there's 31 trees, and of those 31 trees, how many are less than 75? So here's our 75. Going to the left, how many are to the left? We have 2, 3, and 6. So I'm going to add those up. So we have 2 plus 3 plus 6. So that'll give us 5, 6. This will give us 11. So we have 11 out of 31. So if we punch that in, same thing, I'm going to go out to 4, so we'll get 0.351 4. Now we have 8, and then we have a 3 after, so the 3 is not, right? This 3 is not bigger than 5, right? It's not 5 or more, so we're not going to round up that 8, so we'll stop there. We don't need to do any rounding. Just like before, we're going to move our decimal place 2 spots, 1, 2, and this will give us our percentage. So this will give us 35.48%. So I hope you enjoyed the video and learned a lot from this, and I'll see you on the next one.